1 week.
And we have some that were 2 days old. So we can show them a small video screen or an LCD screen and create different patterns of illumination, spots, moving bars. These are the kind of typical things that have been done in similar fields in mammalian models, and look at basically evoked activity due to different types of stimuli for a longer wavelength excitation, and using sort of 2 infrared photons as a single photon through this nonlinear effect, we can excite dyes at excitation wavelengths half the wavelength of the femtosecond pulses. So the wavelength we're using the laser at wavelength around 800 nanometers, and so we're exciting dyes approximately around a 400 nanometer, more or less based on fluorescein. One is called Oregon Green Bapta, another is called Flow 4. All these dyes are commercially available from Invitrogen, which we use. And,
I know.
there are various ways to inject them into the system. But you know, we have collaborators who also look at genetically encoded proteins, like GFP, fluorescent proteins, and other fluorescent proteins.
What is a typical experiment? How long do you keep?
So typically, we image at about 1 frame per second, and in the case of mammalian tissues, we can image for, take a series of images for hours at a time, and we can repeat the imaging and do so-called chronic imaging, so that imaging can be actually done over a course of months with the same animal. With the zebrafish, you could probably take, images for several days. That's about as long as the animal can last in this agarus. And then on the other end, we're also interested in sort of this faster calcium dynamics. So we also want to image at higher frame rates. So we've also have systems that scan at frame rates up to 200 frames per second, depending on how many lines we take. And this would be sort of trying to look at single action potentials with calcium indicators. This can really only be done in vivo with multiphoton microscopy. And 20 degrees Celsius, between 20 and 30 degrees Celsius, there's not much difference in the performance we found. It more or less runs the same stability, same wavelength, everything is the same. Daniel is going to turn on the spectrometer. But right now, he's turning the power. Mode lux. Light turned green, so it's pretty much alignment is very stable over months, as long as it's aligned once every month or so. And the cavity doesn't have to be aligned at all. The only alignment issue is the pump laser. And we get an output of around.
What is the pump power now?
Pump power is around probably 6 or 7 watts. A low-cost, ultra-fast oscillator is something that's very unique for a price of tens of thousands of dollars, order of magnitude less than the commercial offering from spectrophysics are coherent, one can start a multi-photon microscopy right away in a tabletop lab without having to use a core facility or an expensive confocal scanning units from a microscope manufacturer. Multi-photon microscopy in vivo experiments. Power is critical, but I'd say that you can look at things starting with as little as much as 5 milliwatts into the system. And I think, probably every 200 micron or so, every scattering length you go deeper into the tissue, you probably drop off exponentially in return. So, but I think 500 milliwatts is a very good start to using multi-photon microscopy. Excitation spectra is usually quite broad, and I think anywhere within 100 nanometers you can still excite the dye and do your experiments. So plus or minus 50 nanometers is generally a good rule of thumb for excitation width. From in behaving and awake animals and live animals and intact brain volumes, how populations of these neurons encode information past the brainstem and the cortex. So where does this information get integrated? Where does it get compared with previous experiences? And how does it form, or what data format does the sensory information inevitably take in the brain? Companies are making money by producing the large finished boxes, right, that cost $1 million once you add everything together. And a lot of researchers realize they can put something together fairly cheap. So if you can, I think a total complete multi-photon scanning system with commercial confocal scanner will cost you probably $1 million when you add the laser to the scanning system. And bring that down by a factor of 10, say at around $100,000, it's very reasonable for a new investigator to invest in that as part of their personal lab equipment. So